So here we go on part 2 of the 2018 C1 paper, starting off with question 9. So you've got to calculate the maximum percentage error in the weighing of the tablet. So let's have a little look at what information we've got then. So it says we have got a 3-place balance. So when you work out the error in a 3-place balance, you're going to have the smallest division, so that's going to be 0.0005. But you do weigh twice if you read through the question here. Reweigh, record its mass. So you've got double that over 0.5, which is the mass, times 100. So the maximum percentage error is 0.2. Suggest why she did not need to measure the volume of water accurately. Well, because it's the number of moles of absorbic acid that is required, and you can find that from the mass. If you know the mass, you can find the number of moles. Why was it heated for 5 to 10 minutes? To ensure all the tablet had dissolved in the acid or reacted with the acid. Both of those are fine. Bit of a funny question, the next one. You're given the mean titer, and you've got to work out the final reading here. So what we're going to do then is we're going to multiply the mean by 3, and then we're going to take these two values away from it, which is going to give you this value, 26.80. Don't forget, when you're using a burette, this last digit here can either be 0 or 5. And then obviously you're going to add 0.2 onto that to give 27.00. Okay, so the final reading actually is 27.00. Ascorbic acid can decompose upon exposure to air. If the reaction occurred before the titration was completed, state how this might affect the titration results. Explain your answer. Well, if it decomposes, you'll have fewer moles of acid present, and therefore you'll have less moles of sodium hydroxide needed in order to neutralize it. So there's the answer there. Now we've got some straightforward calculations. So we find the number of moles of sodium hydroxide. From the equation, number of moles of acid is the same. Therefore, you've got the number of moles multiplied by the MR, so that gives you the mass of the ascorbic acid. And then you work that out as a percentage of the tablet. So part F, pH. Now this is a tricky one. If you're starting off with 0.01 of H2SO4, when that dissociates, you're going to get double the amount of hydrogen. Okay, and then if you work out the pH, that's going to be 1.7. Oxidation numbers next, pretty straightforward. So +4 for manganate there becomes +2, so there's your reduction. -1 becomes 0, there's your oxidation. Okay, nice and straightforward, that one. Now an equilibrium constant. Again, very, very easy one. Don't forget to put a square there because of the 2 in front of the ammonia. Square brackets indicates concentration. Put the values in, you should get 0.119. The units are the tricky thing. So in effect what you've got is you've got moles per decimeter cubed squared over moles per decimeter cubed to the 4, 3 there and 1 there. If you cancel those down, that goes once, that'll go twice, so that equals 1 over moles squared dm minus 6. When you invert that, you change the sign of the indices, so that becomes -2 and +6. As Kc is small, obviously this is a small value, this is a big value. That means the equilibrium lies to the left-hand side. When the temperature is increased, the equilibrium yield of ammonia decreases. The student said that the reaction is endothermic. Is he correct? Well, if we increase the temperature, then the equilibrium is going to shift to decrease it, that would move it to the left-hand side. So it's the left-hand reaction which is actually endothermic. So incorrect, the equilibrium will shift to oppose the increase, which is left in this case. The system takes in heat and moves in the left endothermic direction. Now we have another moles calculation. This is again a pretty easy one, except they've messed around with the units, as they often do. Let's just shift this out of the way. Okay, so we've got 1 ton. Now we've got to change that into grams. That's 1 times 10 to the 6. Divide by the MR, and that gives me a huge number of moles. The number of moles of DAP, which is diammonium phosphate, which is over diammonium hydrogen phosphate, which is over here. So that is going to be obviously less, because 3 is a smaller number than 8. So you're going to multiply this number of moles by 3 over 8. So that gives you the number of moles there. So this will be the mass now coming out. Initially it'll come out in grams, then you need to divide by 1,000 to change it into kilograms. So again, just take note of the units. So from the answer to that to there, you're going to have to divide by 1,000. And now we've got PV equals nRT calculation. And again, units are an absolute must. You get these correct. So what have we got here then? So we're just going to rearrange to find the volume. Number of moles is given. R is given. That'll be in your data book. Change degrees C into Kelvin. Now we've got 101 kilopascals. That needs to be in pascals. Okay, so that is going to be 101 times 10 to the 3 pascals. Put the numbers in. Your initial answer is going to come out in meters cubed. All right, and then what you're going to need to do is you're going to need to multiply by 1,000,000 to go from there to there. So that's times 10 to the 6, and then your answer will come out in cubic centimeters. Again, tricky with the units. Question 11. So you've got a carbonate, you've got a chloride, you've got a sulfate. So the first thing I would do is I'd add an acid. Now, do not use hydrochloric acid or sulfuric acid, because they might give you an insoluble salt and therefore stop the reaction. If I was you, I'd use nitric acid. So if there's effervescence, then you know that there's a carbonate present. So add the nitric acid until there's no more fizzing. Then split the solution into 2. If you test for chloride ions, you want to add silver nitrate and also some nitric acid before that, although there's already nitric acid there actually. So you're going to get a white precipitate if there's chloride present. And then for the sulfate, you want to add barium ions. So you could add barium nitrate. Don't add barium chloride, because obviously there's chloride ions there. To prove that there's a sulfate ion present, you're going to look for a heavy white precipitate. So you've got to know your reactions of your anions for that one. Now the cation, student said it's sodium because they're all soluble. Is he correct? Well, he's incorrect, because all group 1 compounds are soluble. Also, ammonium compounds are soluble. So how can you tell which metal ion you had? Do a flame test. If it was sodium, you'd have a yellow flame test. On to this next question. You've got to tell them the type of structure available here. Well, you've got a low melting temperature here, soluble in water, conductivity none, solid or a solution, so this means it's got to be simple molecular. B, you've got a high melting temperature, it's insoluble in water, and you've got no conductivity. So it could be giant covalent, which would have a really high melting temperature, or it could be ionic. C, exactly the same again, it could be giant covalent, but because it's a good conductor, it could be metallic, so obviously graphite conducts, so it could be either or. And D, this does not conduct when solid, but does in solution, so that has to be ionic. So what other tests could you do to tell the B and C what structure they are? Um, you could melt them. You need a really, really high temperature, and then the ionic would conduct electricity, whereas the giant covalent would not. And if it was an acid, sorry, if it was a metal, you could add an acid, and you would get effervescence. And finally, suggest why it is difficult to identify material as a metal when it's in powdered form. Oh, well, a bit of a funny question, this one. Well, it's difficult to conduct when in powdered form. It's not shiny, ductile, or sonorous when in powder form. So the properties of a metal in powdered form don't really appear, or certainly they're not obvious. So that's the end of that paper. Tough paper. A lot of places where you would change units from one into the other, but you need to be used to that because it's going to be coming up on next year's paper.